We've seen how large language models, based on transformer architecture like BERT, we explored in #TCM 183004, are incredible at capturing patterns and knowledge. They implicitly store a vast amount of factual information, which is quite powerful.
But store sounds permanent. Does that mean their knowledge is fixed the moment training finishes? What happens when the world changes, or you need fresh, domain-specific data that wasn't in their original dataset?
That's exactly it. The paper states their performance lags on knowledge-intensive tasks, especially in areas like providing provenance for their decisions and updating their world knowledge, two big, persistent challenges for purely parametric models alone.
This paper proposes a solution called Retrieval-Augmented Generation. Let me read the abstract directly. We explore a general-purpose fine-tuning recipe for Retrieval-Augmented Generation, RAG, models which combine pre-trained parametric and non-parametric memory for language generation.
So, retrieval augmented sounds like the model isn't just generating from its own brain anymore. What exactly does non-parametric memory mean? Is it like giving the model an external real-time textbook to look things up in rather than relying solely on its learned parameters?
Precisely. The parametric memory is the language model itself, often a seek-to-seek transformer. The non-parametric memory is a dense vector index of Wikipedia, accessed by a pre-trained neural retriever. It's literally a searchable knowledge base working alongside the model.
This combination is powerful. The paper shows RAG models set the state-of-the-art on 3 open-domain QA tasks, significantly outperforming parametric seek-to-seek models. It truly grounds the answers in explicit, verifiable information, which is a major step forward.
So, by giving the model an external brain it can query, it becomes more accurate and trustworthy. That makes perfect sense for preventing it from making things up. Let's explore why LLMs make things up in the first place.
Even the most advanced foundation models can confidently give you wrong information. This behavior, where they produce confidently inaccurate and irrelevant output, is what we call hallucination. It's a key and very common problem RAG addresses directly.
And one big reason for this is often cited as knowledge cutoffs, right? When the model was trained, its data was frozen at a specific point in time. It simply can't know about recent events, like last week's NBA results or new iPhone features.
Think of it like a brilliant but isolated scholar. They know everything up to the point they stopped reading new books. Ask about last week's news, and they'll either guess plausibly or confidently provide outdated facts as if current. Now, unlike a human scholar, the LLM doesn't consciously guess or know it's outdated. It's simply predicting the most probable words based on the patterns it learned from its frozen training data, even if those patterns are no longer accurate or complete for the current world.
But what if the knowledge exists, it's just really niche, like specialized medical knowledge or company internal data? Does the model just not know it because it wasn't common enough in training, or the data set was too small for that domain?
Yes, exactly. Foundation models have broad knowledge, but often lack depth in specialized domains. Public, high-quality data sets for these niches might not appear enough during training, leading to incomplete or irrelevant responses for highly specific questions.
This also applies, crucially, to private or proprietary data. A general-purpose public model cannot know your company's internal policies or customer data. Including it would be a huge security risk, but its absence severely limits the model's usefulness for custom business applications.
And without knowing where the model got its information, it's hard to trust, isn't it? If it can't cite their sources, we don't know if the answer is authoritative or just a plausible fabrication from potentially unreliable training data.
The root cause is that output generation is probabilistic. Models assign probabilities to all possible continuations, even wrong ones. Combined with sampling randomness, they can choose a plausible but incorrect path, even sounding confident when inaccurate.
So RAG offers a powerful way out of these limitations. By providing the model with authoritative external data, it can generate responses that are not just plausible, but accurate, relevant, and even fully verifiable with citations. So how does RAG specifically address these issues of hallucination and outdated knowledge? It works by first accessing authoritative data sources like proprietary, domain-specific data. This data needs to be meticulously prepared before the LLM even sees a user query.
You mentioned preparing the data. What's the first step for building this external knowledge base? Is it just dumping all the text, like legal documents or internal wikis, into a giant file, or is there more to it than that?
Not quite. First, we chunk the data. If you have a long document, like a detailed company policy manual or a research paper, you divide it into smaller, manageable pieces, paragraphs, or even just a few relevant sentences. This makes retrieval very precise later.
So you chunk the data. Is there a perfect size for these chunks, or are there trade-offs? Because I can imagine if a chunk is too small, it might lose context, but if it's too big, it might overwhelm the model or dilute the specific information needed.
That's a very insightful question, Maya. There absolutely are trade-offs. If chunks are too small, you might indeed lose vital contextual information, making them less useful for answering complex queries. On the other hand, if they're too large, they might exceed the LLM's context window or introduce too much irrelevant noise, which can actually harm retrieval quality. The goal is that good chunking makes retrieval very precise later, meaning finding that Goldilocks size, large enough to retain meaning, small enough to be specific.
Then, for each chunk, we create vector embeddings. This is where our knowledge of transformers from #TCM213004 comes in. An embedding model, often a small transformer encoder, converts text into a numerical vector that captures its semantic meaning and context.
So it's turning words into numbers that represent their meaning, like giving each piece of knowledge a unique address in a conceptual space, so similar ideas are close to each other, allowing for similarity searches?
Exactly. Think of it less like a fixed street address and more like a coordinate in a vast, multi-dimensional space where nearby vectors signify deep semantic similarity. The key difference from a real address is that these coordinates are fluid and contextual, capturing meaning rather than just location. These vector embeddings are then loaded into a vector database.
Once the data is ingested, when a user asks a question, that question is also turned into a vector using the same embedding model. Then, the retrieval component uses this query vector to instantly find the most relevant data chunks from the vector database. This database is specifically optimized for very fast semantic search, finding chunks whose vectors are closest to a query vector, representing conceptual similarity, not just keyword matches.
So the retriever pulls out the most relevant chunks. But what if there are many, or some are only slightly relevant and some are critically important? Is there a way to make sure the best context gets to the LLM?
Excellent point.
Retrieval isn't always perfect. This is where more advanced RAG systems often incorporate a re-ranking step. After the initial retrieval, a separate model, often a smaller, specialized one, will evaluate the accuracy and relevance of the retrieved context in more detail, ordering them so the most pertinent information is presented first to the LLM. This ensures the model's limited context window is filled with the highest quality information.
Okay, so we have the user's question and relevant pieces of external knowledge. How does the language model actually use them? Does it just read them side by side, or is there a specific method for integrating this retrieved information?
That's the augmentation step. We literally combine the retrieved data, often several relevant chunks, with the user's original query into a single, extended prompt. Then, in the generation step, the model generates output from the augmented prompt, using the context to drive a more accurate and relevant response.
This process ensures the model doesn't just make things up or rely on outdated facts. It actively consults a fresh, relevant knowledge base before generating. Let's see how this plays out in a demanding scenario like few-shot learning.
We've seen how RAG grounds LLMs, making them factual. Now, consider a particularly challenging application, few-shot learning. This is where models learn knowledge-intensive tasks with very few training examples, a task where rich external knowledge is absolutely critical for performance.
But for few-shot learning, especially in knowledge-intensive tasks like complex question answering or fact-checking, models usually need massive parameter counts to store knowledge, right? Isn't that what we've previously learned about scaling LLMs to encode more information?
Precisely. But this paper argues that retrieval-augmented models are known to excel at knowledge-intensive tasks without the need for as many parameters. They don't need to store everything internally. They can efficiently look it up from an external source. This paper introduces Atlas, which they describe as a carefully designed and pre-trained retrieval-augmented language model. Atlas is specifically built from the ground up to leverage RAG for few-shot learning effectively and efficiently.
This all sounds incredibly promising, but are there any situations where RAG might not be the best solution or where its effectiveness might be limited?
Absolutely. While RAG is powerful, it's not a silver bullet. For instance, the quality of your retrieved information is paramount. Garbage in, garbage out. If your vector database contains irrelevant or incorrect data, the LLM will still be grounded in that flawed information, reinforcing the idea that RAG grounds in provided data, not necessarily absolute truth. Also, RAG introduces an additional computational step, meaning higher latency and potentially higher costs compared to a pure LLM. And while it helps with factual grounding, for truly complex multi-step reasoning or synthesizing information across many disparate and subtle contexts, it still relies on the LLM's inherent reasoning capabilities, which have their own limits. Lastly, the choice of chunking strategy for your data significantly impacts retrieval quality, and finding the optimal approach can be an engineering challenge.